some notes. Present now. Okay, so in this course, as we said, we are going to cover some or try to work on some problems where we deal with mathematical complexity. And there are two major factors that affect the performance of a specific engine or specific solution that we try to, or the performance of a technique that we try to use to solve a problem. This would be the size of the problem and the problem complexity. Complexity is driven by the type of the approach that we use, and complexity, it can increase from a continuous problem to discrete, from linear to non-linear, from deterministic to non-deterministic. And the classification or categorization made based on the, which is shown here like continuous versus discrete, it is defined, so it is based on the domain of the decision variables. So decision variables, they can be defined in a continuous domain or in a discrete domain. So discrete domain, it's the same way like as we define the Boolean variables, which represent a special case of, let's say, DD, which is a grade, probably. Or, but it can be represented numerically with a specific assigned value. So if it is the number of students, it's going to be a discrete domain. If it is a continuous, you can find any value on the real number space. Let's call it this way. And the problem is continuous if the decision variables are continuous. In this case, linear programming algorithms can be implemented or can be used. Problem is discrete if one or more of the decision variables are discrete. So if you have one variable is discrete, the rest can be continuous. The problem is defined as a discrete one. And generally, this type of problem is called mixed integer problem. And these problems are solved by solving a continuous problem for each enumeration of the discrete variables. We have mixed integer programming. Mixed integer programming, it's much more complex than linear programming. And there are some toolboxes which are implemented in different programming languages, such as Cplex. And this specific optimizer, it uses a method which is called branch and cut. This branch and cut, this is an approach actually which uses combinatorial calculations to determine additional constraint called cuts. Now, for next week, we are going to assign someone to talk about the travel in salesman problem, and that one has also a solution which is similar to this branch and cut. It's not difficult. It's just an approach of how to solve the problem step by step. And the combinatorial calculations that can be used to determine the additional constraint, which are called cuts, which are implied by existing constraints and the finite domain of the variables. These cuts reduce the size of the solution space that the algorithm has to search. Okay. Now, the algorithm, it can set up a search tree actually by successively assigning each discrete variable to one of the possible value. This can imply additional cuts. And okay, maybe it's not, I can give an example later. And at each node where we design or where we define a new cut, the algorithm solves a linear programming that approximates to the original solution. The solution may find a discrete optimal solution better than any found up to that point. Or this solution, it can provide an upper or lower boundary with regard to the problem based on what we are trying to optimize. Okay. Now, if neither of these events occur, then the algorithm, it will create new branches in the search space or in the search tree that corresponds to the possible value of the next discrete variable. Now, we have also the problem of linear problem versus non-linear problem. Now, simply stated, a relationship is not linear if it's not linear. Now, a linear relationship is anything which has to the power 1. So anything that can be solved using linear algebra, we call it a linear problem. So we can say that you may have the cost of the books, of the desks, of the pence of the food, this you add a constant value, which is the price, plus the amount of quantities that you are going to obtain. This defines a linear relationship, okay? So when you have an exponent of 1. And nonlinear problems, they are much more complex and harder to solve, and they need a powerful optimization algorithm. Now, the nonlinear problems, we often use numerical techniques how to solve them, but this is not the complete objective of this course. I mean, it's not how to solve using numerical approaches. For this moment, we're just defining different types of problems. We have also problems that are deterministic versus stochastic. This is defined based on the certainty of the input data. So if we know all the input data, the problem is deterministic. If some of the data is not well defined, this would be called stochastic. Now, stochastic problem, often they can be solved by, the solution can be offered by solving several deterministic problems. Okay, so we might change the input data randomly, and we define that problem at that point as a deterministic one. And solving this, we try to find a solution which can cover the stochastic option. Now, then we move to algorithms, and algorithms are based on the complexity. They can be defined as P versus NP, and the algorithm they can be defined as exhaustion algorithm, where the best solution is found by examining every possible solution. So we do a brute force. So we check all the options, and maybe we try to optimize what we were given. And for these types of problems, for these algorithms, the complexity it can be in n factorial. Then we have polynomial time algorithms, where the complexity, or the f of n, is in the order of n to the power k for some fixed number. But this is still polynomial, because a polynomial by definition is any quantity which is a to the power x plus b to the power x squared plus c to the power x cubed and so on. So this x to the power cube is n to the power k. For example, we have a classical excellent problem, which is a Hungarian algorithm. Actually, we can remove here transportation. In the second part, this is not Hungarian transportation algorithm. It's just Hungarian algorithm. This one has a complexity of n squared. Complexity of n squared, it's really good. It's a good one, which means it's solvable by n, easily computable. And we have also the exponential time algorithms, where f of n is in the order of 2 to the power n or 3 to the power n. And these are very inefficient, because that means that we need a lot of resources to find the solution of a problem. The problem can be 3 by 3, so you can have 3 variables. Then you could solve it, okay, using brute force. But if the size of the problem goes from 3 to 10, then maybe it has no solution. The polynomial time algorithms, which is the second set of algorithm mentioned in this slide here, they are tractable, whereas the other exponential time algorithm, they are intractable. To show a problem is intractable, we need to prove that no polynomial time algorithm for it can exist. Even this proof is difficult, okay? So actually showing that the solution cannot be offered, it's hard even to prove it, because we have to exclude all the possibilities to solve it in polynomial time, okay? Now, even expressing this in an elegant way might be, sometimes it might be challenging. Problems that require polynomial time for both solving and checking, they are called as P problems. Okay, so this is essential. The class of problems where the solution requires exponential time and the checking of the solution requires polynomial times are called NP problems, or non-deterministic polynomial time problems. So let's see this again. It looks like solution requires exponential time, and the checking of the solution requires polynomial time. Okay, so let's say we need a long time to find it, but to test it, we need to test that we really found the right solution. It might take a polynomial time. This is called the NP problem. We have also NP complete problems, which is the subset of NP problems. Now, this type of problems, there is no polynomial time algorithm that has been found yet for any of these. No one has yet proved that polynomial time algorithms do not exist for any one of them. If a polynomial time algorithm could be found for one of them, then polynomial time algorithm must exist for all of them. So what do we mean with this? There are some problems that can be classified as NP-complete. Good. It's a one type of complexity. It's hard to compute. You don't have enough computational power, let's say, to calculate, okay? Let's say these problems are 4. Now, if we can solve one of these category or class of problems using polynomial time, then if we solve only one, then we can solve all 4 if we have 4 problems, okay? Which means that because it is possible to use a transformation function, or you can redefine the problem, if you have NP-complete, here you have the set, you solve one, you solve all of them. Good, because they can be represented in terms of each other. If it could be proved that no polynomial time algorithm exists for one of them, then no polynomial time exists for any one of them. So again, we have the same set of problems here, like to test whether, for example, factorization problem, to check whether a number can be factored as a product of 2 primes, or primality test, to check whether a number is a prime number or not. These are the types of problems we are discussing. And what happens is that sometimes one problem can be can change a subset. One problem that is NP, if we find a solution which can be solved in a short time, we can upgrade them, and we call this polynomial time algorithms. And once each time the researchers or mathematicians or computer engineers, computer scientists find a solution of bringing down one NP problem to a P problem, this is a huge gain, or everybody would make use of these new algorithms. But the last statement is, the last 2 statements are actually very essential, which say that we have a set of problems, all of them are NP-complete. If we can prove for only one of them that no polynomial time algorithm exists, then this proof is valid for all of these problems. And as we said before, even proving the existence of or non-existence of a polynomial time approach, it's very difficult. For example, traveling salesman problem is NP-complete. This TSP, actually, which we are going to describe, maybe some of you might have already, for sure, actually, most probably you have heard this one a few times when you did the analysis of algorithm course during the 3rd year. And the traveling salesman problem is both NP hard and NP, and this implies that this is also NP complete. Now we have another problem which has the same number of complexity, we can call this way, which is called the assignment problem. This is a relaxed traveling salesman problem, and this has a much shorter computational time. Now, TSP, the traveling salesman problem, this usefulness is illustrated in these examples, such as computer wiring, vehicle routing, crystallography, robot control, drilling of printed circuit boards. Actually, this is very unique. This problem of drilling of printed circuit boards, this can be defined as, let's say you have a circuit board, okay, and you need to drill, like a PCB. You have a PCB or a flat plate, and you need to connect certain capacitors and certain operational amplifiers on this circuit board. But let's assume, for example, actually this traveling salesman problem, we can pose it also this way. Imagine for a moment, you have a PCB, and you need to connect, let's say, you need to connect 5 operational amplifiers, okay? 5 operational amplifiers, each one of those, so 5 op-amps, okay? And each op-amp, it has 8 connections, okay? So we have 8 pins, where one of them could be the input, one is a clock for some operations. So we have 8 pins per op-amp. So if you have 8 pins, and then imagine that you need how many pins? We are defining drilling as probably laying material, conductive material, so that you can lay over an op-amp. Okay, so op-amps in electronic circuits courses, there are these these chips, little chips, which allow digital input, digital output. So imagine you have 5 operational amplifiers with 8 pins. This makes a total of 40 pins or 40 connector stations. not station, points, let's call it points. Now, this is 5 by 8, it's very easy actually. I mean, really putting down, let's say, 5 op-amps, it's relatively, it doesn't take much time, but imagine that the PCB looks like this. You need to put one op-amp here, one here, and one you need to use somewhere here. And you are given the location of these op-amps, and then you have to find out what is the shortest path that the drilling machine is going to use. Imagine that you put a PCB here, and you are going with a machine. You have motorized it, okay? So the machine goes, it drills something, then it goes to the next one. Imagine for a moment that you want to describe the shortest path that you need to make the connectors for these necks. So if it has 8 pins, you have 4 on one side, 4 on another side, good. And the multiplication, we have done this correctly, okay, which means that we have 40. Now the question is, how can we find the shortest path? The shortest path is defined, let's say, we do this, this. So this is defined, the total length is defined by how much the drilling machine is going to move on XY plane. Okay, so this is sitting here, it's going to move across like this. So I'm going to move like this, I drill this here, again, then I move here, I do something here. So calculating, the question is, find the shortest distance. How can we do it? I mean, how long can it take for a machine to do this? I mean, a machine, if it is motorized, even if you do it by hand, this will take half an hour, depending how much work you are going to do, right? You're going to sit on 40 different locations. But then you might think this way, you know, I'm going to optimize this problem. I'm going to find the shortest path for a machine to drill these. Then let's sit down and find the shortest path, which is defined as follows. You have one pin, then you have to calculate all the rest of the pins. You have one, you decide one, then you are left with 39 possible pins. You decide the other one, then you are left with 38. Then you pick one of these, you are left with 37. So the number, if we just want to add the addition between the distance between any two subsequent pairs, we need the number of calculations is going to be 39 factorial. Okay? So 39 factorial is the distances that we are going to add together, and we have to combine. We have to figure out whether dealing this and this and this is shorter than starting this. Okay? Now 39 factorial, let's assume that we have to add all of these numbers. What is 39 factorial? We can try to identify this one, and also let's see how fast we can do these calculations. The speed of calculation is defined by the speed of the computer. Nowadays, we are at the speed of gigahertz, so we can do 10 to the power 9 calculations per second. So if we divide this one 10 to the power 9, this is calculations per second, okay? Then this is also calculation, so we cancel out calculations. We can find how many seconds we need to find what is the shortest path. Then after we find the shortest path, we can tell the machine, you know what, if you're going to drill 100 boards with electronics on top of it, use this path. But now let's find how much time does it take for us to determine the shortest path. What is 39 factorial? 39 factorial, let's start from 39. This is equal to 30 factorial times 31 times 32 times 33 times 34, 35 up to 39. So all of these that we wrote here, this is 10, we have 9 tenths. 10 to the power 9 is that we have a lot of tenths. So you can cancel out all of these, right? So you cancel out the 10 to the power 9, we're left with 30 factorial, or 29 factorial. So let's try to identify how large is this number. And we see that if you calculate, any guess, anyone could have any guess, what is this? If we use a calculator, we can use it also by hand. And we don't always need to do this, but 5 factorial, it's 5 times 4, 20 times 3, 60, and 2, 120, okay, we are 120, times 6, this is 720, times 7, we get 1,000. So you can use a calculator and see how much your calculator can calculate. If you have the factor, if you have the factor, how can you do this? My calculator doesn't have it, but anyone? No, I'm. So you can use an exit or something, but can someone come up with a number? So I'm sharing my screen, so let's have a look for a moment. What is 20 factorial? Factorial value. Factorial, it's a number which looks like this. It is 1, 2, 3, 4, 5, 6. So this is 6 tenths. How many? This is 2 times 10 to the power. I don't know how to count this. This is 1003, 1006, 1009, para controlar. Para ver 8 1, 2, 3, 4, 5, 6. Para 10 So 20 factorial times 21 up to 30. This itself, this is 10 to the power 18. Okay, 10 to the power 18. Now, what is this? Let me think for a moment. These are seconds, and we can find how many seconds are in a year. I think it's something like 10 to the power 13, but I'm not sure. No, okay. So 1 year has 10 to the power 7 seconds, okay? 10 to the power 7. So if we have here 10 to the power 18 seconds, divided by 10 to the power, is it that? Okay, it's 7. Is it a year? I'm really having a calendar year. Yes, that's true. If we divide this with 10 to the power 7, we get 10 to the power 11 years, okay? So we did not even calculate, this seems a little too much, but I even doubt this one actually. Is it, how many seconds are in a year? Yeah, this is really 10 to the power 7, okay. So apparently, it looks like we need 10 to the power 11 years, which is a lot of lifetime, which is almost larger than the, what is the lifetime of the universe? It's billion. Billions, millions is 10 to the power 9. So it looks like it's 100 times longer than the lifetime of the universe. Okay, so this makes it really a challenging problem. So we better, rather than telling to the machine what is the shortest path, you better do it randomly, because calculating the shortest path, it would be almost, not almost, we cannot solve it, okay? And we just assume 5 operational amplifiers with four connectors at the bottom. So this is a drilling printing circuit board, and this is also defined like traveling salesman problem, which is defined as a driver who travels 20 cities in our case, and but he has to travel such that he saves the largest amount of gas, so he should cover the shortest possible path. And he can do it in a week probably, but deciding which is the shortest path, he'll never be able to calculate it. So this is the type of really how complex the problems can be. Now, this the best approach, or one of the approaches nowadays, which is not the best, sorry, it's not really the best, but well-known computing method is the branch and bound algorithm, BNB, which is used, and it's you can find this publication here, which is published in '54. It's an old publication. And now the thing is that if someone can solve the traveling salesman problem, then one can apply this solution of this problem to other optimization problems. For example, and now the thing is that if we have let's say if we have 20 cities or 21 cities, for 21 cities, the number of combinations is 20 factorial. Okay, this is the size of the problem. Sorry, we're looking at the screen, so you can see the monitor, but I think you can pin my camera, I guess, and you can see what I'm writing on the board. So if you have 21C, this is the number of combinations. And this is TSP, okay? But there is another problem which can be defined as follows, which is having 20 workers, or let's say having 20 workers or 20 students in one class, and to each student you want to assign one problem. You have, at the end of the chapter, you have 20 problems, okay? Problem 1, problem 2, up to 20. Then in the class you have 20 students, you assign 1 to 20, and then you want to ask the students, you ask them, which topic did you study? You say, I studied operational amplifiers very well. Okay, so you do operational amplifier. But then you might say, I can solve the operational amplifier problem in 2 hours. I can solve Ohm's law in 7 hours. And I can solve another problem in 11 hours. So they write all the times here, okay? And another student might have other difficulty levels and he assigns different numbers. And imagine that you want to posing this problem, which is called the assignment problem. Posing this one, this is defined as follows. Identify how we have to distribute the problems to 20 problems at the end of the chapter to 20 students, such that it takes the least amount of time. Now, when you look at this problem, we see that we can assign to the first student 20 options. Good. Let's say you assign one problem, you pick this one. Then to the second student, he is left with 19 choices. So you get 20 initial. The second student, you can assign 19 choices. So 2 are gone. The third student, you can give to him 18 different problems. So it goes like this, 20, 19, 18, up to 1. So the total number of options is also 20 factorial. 20 factorial here, 20 factorial for traveling session problem. This one can never be solved, at least until now, in polynomial time, but the assignment problem, this is solved, because the complexity, to solve this one, the complexity, it has been brought down to n cubed for a few years. Then, after a further optimization, they brought this down to n squared, okay? And this is an example of 2 different problems that carry the same order of complexity in terms of the number of possible assignments or possible paths. Okay, so in traveling session problem, you can define this as a path. You say that you first connect this pin, this pin, this pin, then you go here, then go to the other one. And this is defined as a assignment problem. So with the same number of paths, we can determine this one very fast, but this one not that fast. Now, in terms of transforming one problem to another, it would be amazing if we can formulate the traveling session problem like an assignment problem, because once we do that, we can use the transform function that we solve this problem in n squared to solve also TSP. So far, we have not been able to do it for some problems that have been thought for a long time that they cannot be solved in polynomial time. Some of these problems have been solved, and what happens with those, we just remove them from the family of NP. We say, okay, now this is a P problem. Good. So this is what we're trying to explain. And the algorithm, let me see, I think this one we can cover the next time, possibly. Or at least we can have someone of you go over this one. Go over the history of the Hungarian algorithm, which is the best solution ever to solve the assignment problem. Stop presenting. Okay. I apologize here, power of 10. I have missed the comments of Ari and Johan, so sorry, I was... Okay, thank you, Johan. And okay, so we are discussing now about the complexity of this problem, and more to what we saw on the slides, we can say that so another complex problem is the click problem, which is a strange, unique problem. Now, a lot of these problems what's strange is, I mean, anyone can try to solve those as long as it is brute force, but we don't want to do brute force, so we want to do something smarter. So the problem is that we want to find the best option without searching all the options. So this is what we're trying to do. So this is a different problem, and I think we talked about that NP is a non-deterministic time problem, and we said that also around 2001, a professor at the university asked two students from India, asked them, can you go over all the algorithms that are currently that checks whether a number is a prime number or not? But we are talking about large numbers too. Okay? So we're not talking about the numbers that we can find in the multiplication table. And these two students, they went over all the algorithms, and then they figured out a solution, a very unique solution that was not offered yet. And they figured it out, and the primality test, they brought into a computable time, and they were even invited to the United States to present their work, but they could not go because they did not get the visa on time. Okay? These were Indian students, and they figured out that to check whether a number is prime, so prime number, to check whether a number is prime, they have to analyze the following. So, for example, you want to figure out whether 7 is a prime number. This is the question. And in order to do this, we start by dividing all the prime numbers that we have on the list. Rather than doing this, we can, one can try the following. If 2 to the power of 7 minus 1 is equal mod 7 is equal to 1, then we call this one a prime number in the case of 7. So we have to check, in general, we have to check the following, or more generally, we can pose this problem like this. P minus 1 is equal to 1 mod B. Okay. For example, 2 to the power 7 minus 1, this is 2 to the power 6.
This is true. That gives 127, which minus 1 is 126, which is perfect divisible by 7. So yes, that's
true, right? Okay, thank you.
It checks out, yes.
Okay, so this is true. So yeah, these students, they came up with this solution, and it ended up being true. But thank you, Ari, for the comments. So we can also check, for example, 13 and so on. But wait a second. But Ari, you said 2 to the power 6 is 2 to the power 6 is 64. It's 64, I guess.
Oh no! It's 2 to the power of 7 minus 1 in the power. No, sorry. I thought 2 to the power of 7 minus 1 down there.
No, it's like this. So 64 mod 7, we really get 1. Okay. Mod 7, we get 1 because 66 times 9, 7 times 9. Yeah. So this is confirmed. Okay. So this is what we see. So this proof of this brilliant students actually that just help us into determining faster whether a number is prime or not. So when someone is trying to express a large number, as a factor of 2 primes, if someone is scanning all the possible numbers, they could always apply this technique, and they can define much faster whether they have the right numbers or not. Okay. So, and yeah, that's. Okay, this is the definition of the problems. Now, I want to stop the recording at this. No, sorry. I think we can stop the class at this point.